Okay, so the plan will be today, we finish talk about the water. We left something we want to talk using chalkboard, and then we want to go over the slides using the traditional methods to talk about slides. Then Thursday, we're going to jump into about the protein section. We'll talk about amino acids, the basic knowledge. Next week, Tuesday, Dr. Kenny will give a talk about the amino acids and the muscle protein. Then next week, Thursday, we will talk about the very important information is the Maillard reaction. And then the following Tuesday, we'll have our exam 1, which is an open book. Okay, so I'll send a notice email before that next week sometime. So let's talk about some of the water. We already finished talk about the majority of that. So let's do some of the review. We talk about the water molecule. So it looks like this. Covalent bonds connected with hydrogen bonds. We call it theta, negative, positive. So we talk about structure, then we talk about the sp3 hybridization, okay, sp3 hybrids. Then we talk about the very important curve, which is we call it sorption-desorption isotherm, and we have x-axis is water activity, y-axis is equilibrium moisture content. So the curve looks very interesting. It looks like this. And we say this is a sigmoid. We call it hysteresis, which means sorption-desorption is not completely reversible. And then we mention about a very good theory to explain that is an ink bottle theory, which is pointed by Dr. Labuza. Because we think about the sorption, it decided by the bottom, the radius, and the desorption decided by the how thick the radius of the neck. And then we mention about several equations, mathematical equations to explain the sorption-desorption isotherm. So we have a sorption and we have a desorption isotherm. We talk about the Langmuir equation. We talked about BET equation, which is by 3 scientists, 3 also Bruno, Emmert, and Taylor. And we also talk about the most important is GAB equation, Guggenheim, Anderson, and De Boer. And we also talk about the modified GAB equation very briefly. That could be explain covering all of the food products range from 0 to 0.99, the water activity. We finish this water, then we mention about the ice, and we talk about the very important thing is the nucleation and versus crystallization. We mention about the relationship between nuclear number and also with the crystal size. And we had a very important curve. It looks like this. That is important. And this is temperature. Y-axis, x-axis is a crystal size. And we mentioned about if this curve long and long, and when it's reach minus 40 degrees Celsius, then we will say at that temperature even we have a free water, which means nucleation is 100% will happen. Okay, so of course we talk about the ice structure. So that's what we have briefly what we reviewed. And today we want to talk about something else. We want to mention the first thing is phase diagram. So we know there is a three status of water, which is liquid, which is could be solid, and the liquid could also directly become vapor, and also the solid products, solid like ice, could be directly become vapor. So therefore, it comes out a very important curve in the chemistry. We draw it like this. We draw it basically like a rectangle or square. So x-axis is temperature. That is degree Celsius. Y-axis is pressure. Now, the pressure what we're using is millimeter of mercury column. And then we had an important curve is looks like this. And then we can draw right in the middle. And this line is corresponding to 0 degrees Celsius. So we can separate these into, this is minus 10 degrees Celsius, minus 20 degrees Celsius. Goes here, we have 10 degrees Celsius and 20 degrees Celsius. Here, the important thing here is this is 5. Then we get this one minus like 10 right here. At the top, we get 15. Okay, so what are the position of those three phases? So we're going to have a liquid right here. We have a solid right here, and we have a vapor. So therefore, we come out with the three important lines. The first line is right here. And the line, we could say this is a TC, and this is A, and this is B. So the first line here is a TC line. That is a melting line. So we can review back what we learned in the physics. If the solid become liquid, let's say ice become the water, this is what we call melting. And everybody knows. And we have another line which is TA line. TA line, which is right here. That is a line, is basically is a liquid become vapor. This is we call vapor pressure line. And this process we call vaporization. This is, we know. But there is something could happen, is the TB line. The TB line is important during the food processing. The TB line, which means the solid products, could directly become vapor. And in the physics, we have a terminology called sublimation. So this gives us a very important stuff. If we have a product at 0 degrees Celsius, and we mentioned this 0 degrees Celsius is coexisting of water, but don't forget, and ice. We can say sometimes a little bit lower than 0 degrees Celsius. So majority of them ice. And we want to melt in the ice. Okay, if we, oh sorry, I made a mistake. That's too opposite. That's why I was confused. This is solid. That is liquid. the ice will can directly become vapor. Based on the curve, what you can see is basically right here, is this point, which means a little bit lower than 5 millimeter mercury current. So what is this? Melting ice, a solid status, at 0 degrees Celsius, but the pressure is less than 4.8 millimeter mercury current. The ice will directly become vapor. You can understand it's become like a gas. This is extremely important. This is the principle behind a very easy but important procedure is freeze drying. And we have this machine in the lab. So Dr. J and Dr. Martak is doing the research about the insect proteins. So we try to recovering those we say a waste protein become a variable protein resource. So what they do is using a freeze drying, and we'll get those powder, becomes those solid products will directly become a vapor. And the left one is a very high nutrition products. Then those freeze dried products, we could send it out to test the amino acid profiles and the sugar, carbohydrate profiles, and all kinds of things we could test it. And lots of them we find it's a high nutrition value about that. So this is the important thing, which is a very simple curve in the textbook, but this tells us. The key thing is that 0 degrees Celsius, if we have a pressure which is less than 5, approximately less than 4.8 millimeter per mercury current, and then you see the solid will directly become a vapor. Okay, so something background what I'm gonna review for you. 76 millimeter mercury current is equal 1 standard atmosphere pressure. Okay, that's the physics. That equals 1.03 multiplied by 10 to the power of 5 Pascal. Now, in the older time, people are using so-called torr. So 1 torr is equals 133.3 Pascal. So you can go ahead to do the calculation in the old time. But the research what they do is using the mercury column, how high it is, because coming from this basic equation. Okay, just I want to explain this to you. Okay, next one. We are doing lots of the research related to antimicrobials. The detailed mechanism of antimicrobials we will introduce to you later. Today we want to talk about one thing, is the chlorine water. Because that is widely used in the food processing, and there is some misconception about it. Okay. So we want to talk about chlorine water. There's lots of the chemistry behind it. So first of all, chlorine water, why lots of people use it? So let's say you have a bottle like this. Okay. The chlorine water bottle, this is usually only like $5, 1 gallon. Then lots of people, what they do, they will prepare a container. Okay, they just dump in, and they mix it, and then they do go ahead to do the cleaning. But there is some misconception about it. So the chlorine solution is not 100% chlorine. The major components is HClO, hypochlorous gases, in a commercial products is about 5.75%. And the approved using, which is up to 200 parts per million on food contact surface. So the first thing first, there is a calculation about that. If the 5.75% products, how you dissolve in the water solution become 200 parts per million. And this is important. It's not just you dump in, then you do it. Okay. The second thing is that we also need to know chlorine solution is highly affected by organic matter. Organic matter, you can understand, is those debris, dust, debris, even those like nutrient solution. Those are organic matter. Even the sugar there is organic matter. So what happened is, if you are preparing 200 parts per million chlorine solution, if in the container, which has high organic matter liquid, so let's give a very simple example. If you have like lettuce juice, ,200 parts per million could decrease to less than 0.5 ppm, only need less than 1 minute. So it is highly affected by the organic matter, which means when you're preparing the chlorine water or diluted chlorine water, this bottle or this beaker or this container has to be very clean, which means no organic matter products. Now, how to measure organic matter? There is 2 ways to do. One way is very easy, is measuring NTU, which means turbidity. The second way we can do is measuring chemical oxygen demand. This is digested methods, need a water bath. Then we have standards, and using color spectrometer, we can measure in that. Very similar to like measuring the protein concentration. So this is a thing we want to measure. Now, important is the chemistry reaction. So what's a chemistry reaction here? We had a chlorine water. We dissolved in water. It will become HClO and HCl. So there are 2 products will be coming out. This is we call hyperchlorous acid, and this is we call hypochloric acid. But this product is basically dominant. Okay. However, we want to say is this HClO is highly affected by pH. So there is a very standard curve comes out in the microbiology textbook. Is people they tested at a fresh produce company in telephone about a decade ago. So x-axis is species of chlorine, and the y-axis is pH. So what's the curve looks like? The curve looks like this. right in the middle is pH around 6.8. So we have this pH 6 here, pH 7 right here. Then we have 5, 4, 3, 2, 1, 0 right here. Then this goes 8, this goes 9, this goes 10, 11, and 12. So we want to say that this, if you buy a hypochlorous acid solution, a chlorine solution, you directly dumping the water, you dissolve it. The pH is roughly 10 and 12. This is a new bottle. At that moment, what is the dominant species of chlorine? The dominant species chlorine is chlorine ions. This we call chlorine ions, which means it's not the most effective antimicrobial item. The most effective antimicrobial item is hypochlorous gases. And this we refer to free available chlorine solution. Now there is another thing what we talk about is the total chlorine concentration. That means everything. Okay. Now what else we missing? Because chlorine is very easy to be affected by the organic matter during the fresh produce washing process. So what they do, once the mold produce their washing, and the chlorine concentration going to be decreased. When they decrease, they re-add the free chlorine. And what happened will make the pH value decreased. Then once the pH decreased, the curve is go the other direction. This curve is chlorine gas. So here is chlorine gas. We don't like that. This is intimidation, irritation of your eyes. So what happens is if you're working in a fresh produce processing plants, if you keep doing that, you do not wear any of the goggles to protect your eyes. You're gonna have tearing after like a couple of hours because of the chlorine off gas. So this equation we can also do is HClO will go this direction, become ClO, and could go this direction is become chlorine of gas and water. This is usually is pH around 4 to 5, and this is usually the pH is more than 9 to 10. Okay, so the middle one of the VSA is HClO. Now, how we get to pH 6.8? There are two methods of using. In the fresh produce industry, they are using citric acid. They are adding usually like 10% citric acid to buffer the pH to 6.8. So citric gases, we talk about that. CH2, go here, OH, COOH, CH2, go COOH, that's citric acid. Remember citric acid cycle? That's citric acid. Now, in the poultry industry, what they do, they are not doing citric acid. They are pumping or bumping carbon dioxide. Once you're bumping carbon dioxide, it will become H2CO3, hydrocarbonic gases, and also lower down the pH. Usually the pH is really not exactly 6.8, and they are around like 6. And because they want the dominant solution is HCl. So these are some chemicals behind it. Now it's highly affected by the pH. So next question will be, how about temperature? Temperature effect is minimal, because we wanted to know the temperature. Whether we're using warm water to help or not, it's actually not really. So then another curve comes out. It's a very interesting study what they did a couple of years ago. It looks like a rectangle, and there's a y-axis right here is HClO percentage. And then they go 0, 10, 20, 30, 40, 50, all the way to 100. And there's here, what they do is they go opposite direction. Okay, they go opposite direction. They go here. So this is 100. Above is 0, and then you have 10, you have 20, you have 30, you have 40, 50, 60, all the way to 100. And this x-axis is still pH. So what's the curve they have? The curve what they have is, the pH of course is like this. Let's say 1, 2, 3, 4, 5, 6, 7, 8, 9. The curve what they have is we want to see here is that it looks like this curve. This is a curve at 0 degrees Celsius, which is a very cold chlorine water. Okay, if the temperature we are increasing to 20 degrees Celsius, a little bit higher or close to the room temperature, what's the curve looks like? The curve looks like this. So just shift to the very minimum, shift it a little bit. But all these other chemistries all follow. So the temperature impact from cold temperature to room temperature, the impact is minimal. It's not really that strong compared to pH, the impact of the pH. The pH is important. Now something else I want to say is that chlorine is forbidden in some of the countries. In European countries, the chlorine is not approved to be using. Because the chlorine, if you repeatedly using, they will generate chlorine byproducts. So what are the chlorine byproducts? The very typical one is THMs. That's called trihalomethanes. A lot of the chemicals behind it. It also could generate chloroform. It also could generate bromoform. These are under haloacidic acids. On and on, there are lots of the chlorine byproducts generated. They say they related to the kidney disease and also the bladder disease, also called be a carcinogenic material, but they don't have a variation for the variation for that. So chlorine is forbidden in some of the country, in European country. Therefore, they still like the hypochlorous gases, but they don't want to using the traditional chlorine solution. So what they do, they created electrolyzed water solution. So what is that? This is kind of very interesting, and it's creative, about 30 years ago. So in a water solution, they make it be charged. It become a positive and also negative charge. And inside of this water solution, what they add salt, sodium chloride. Now, of course, the sodium chloride has to be food grade. Okay, you cannot using chemical grade salt. So sodium chloride, what happens is it works with water, with electricity, or electricity. Then what we will generate, they will create HClO and NaOH, hypochlorous acid, and sodium hydroxide. And they think this guy is a sanitizer, and this guy is a cleaner, so it's like a detergent. And they can do both. And on the full contact surfaces, you could be happen is generate the NaOH to clean the surface first, to remove the organic matter, and then they're using the sanitizer. Now, how it comes out? Usually, what happened in this positively charged area, we call it anode. This will be the ClO negative goes in and connected with a proton become this. And then in the negatively charged area, we call it a cathode. And the cathode will create is the positively charged sodium, and with NaOH will comes. That they can connect it together. And they think about this water, and the electrons they will generate is a limited amount of hydroxybase and also the proton. They could be a charged proton, they could be generated. Now the challenge what they have at the beginning is, because they're going through the electricity and continuously to do. So this guy will be dramatically comes out. And also when it comes out HClO, it is still acid. Okay, so both of these are acid. Now what happened? The pH of the electrolyzed water is very low. The pH is around 2 to 3. So all the time we also call it acidified electrolyzed water. And you know the low pH can kill bacteria. Yes, it's very effective. But how about the people who handle that? It's very corrosive. That's not for the so-called occupational health. It's very corrosive. So what happened later on? Later on, people put a membrane there, right in the middle. Using the membrane filtration technology, we try to mix them in appropriate amount with this sodium hydroxide and with a huge amount of acid. So we become a non-acidified, and we just say neutralized, electrolyzed water. But what left the tricky thing is, Is that really going to generate the chlorine byproducts? For some of the reason, I started to do that when I was in the other university about 12 years ago. Because I came here, so the research was being terminated. I didn't do that. It's interesting to do. Is the chlorine byproducts will be created? Is that going to be the same amount? As far as I do the literature review, it's still going to generate those, but the amount will be a little bit less. So that's very interesting. And in the European countries, the electrolyzed water is used widely as a replacement of the chlorine to do the produce sanitizing. And the principles is just here. And it's a very simple facility. And you can buy this one at Amazon, maybe $100 for that, with acidified products. But with neutralized one, might be expensive. It's already been commercialized. But 30 years ago, even like 40 years ago, this is like a creative material for the electrolyzed water. Okay, so this is, we end up with the material we talk about using chalkboard